I've been given the formidable challenge today of presenting two papers on quite not necessarily a smooth transition in ideas between the two. So I think what I'll ask for is, Charles, if you could remind me if we get to 550 and I still haven't switched over, then I'll switch over to talking about a very exciting second idea, which is actually with a co-first author called Chirag, who's lovely, and it's all about estimating example importance and how do we surface automatically examples for human-in-the-loop inspection. But to start with, since this was a special request, I will be talking without lovely slides, but I think that's almost better for this type of paper. I'll be talking about a project that I recently shared, which is called the Hardware Lottery. And I think that this project, I don't know if slides would do it justice, because in some ways it's really about this idea of how our choices about hardware and software have really had implications for the direction of research and the progress that we've made. What I will invite, because of that, is a lot of questions. So maybe what I'll start with is telling a little bit about how I arrived at this idea, because I think it's always fun. You can always go read the paper, and in fact, maybe I'll just present the background of the paper behind. So, but perhaps it's fun to start by talking a little bit about why I came to this idea and why I took the time to write it down. So a lot of my research has been on the topic of beyond test set accuracy. So there was a question earlier about should we care, so we should. So a lot of my research has been how do we train models to not just have high test set accuracy, but to also essentially have interpretability, fulfill fairness requirements, be compact. And compactness is interesting because the area of compactness research, there's almost two different motivations you could care about. So one is this idea that you want to arrive at a theoretically most compact representation of the network for the task. And a lot of people are interested in compression for that reason. What is the minimal amount of weights or minimal amount of neurons we can have in order to still perform and converge well on a task? There's another motivation, which is that if you have compactness, it really helps in deployment. And so one reason compression is really exciting is because you can democratize AI in much more resource-constrained environments. And I came into this research area caring about both. I'm really interested in how we can design more theoretically anchored algorithms where we achieve higher levels of compression, but I wanted to translate. I grew up in Africa and I really want these algorithms to work in the resource-constrained environment of low memory, expensive data. You often don't have a place to charge your phone. And what was interesting is that the hardware lottery really started because I was trying to figure out how does my theoretical work translate? And that might seem like a simple question, but it actually became kind of an 8-month odyssey, an exploration, because what I found was the more I asked, the more people said, well, we're not quite sure. So there's some things we do know. So for example, a lot of compression research is focused on unstructured sparsity. And what that means is that you're removing weights of a network rather than neurons, filters. And unstructured sparsity, we know, achieves high levels of compression. So a lot of people theoretically are very excited about it. But it doesn't translate to current hardware because sparse matrix multipliers are actually very expensive. So we know things like this, that the hardware is stacked against certain ideas, but there's other things in the software. So for example, TF-Lite was mentioned. TF-Lite is wonderful, but in TF-Lite, if you want to work in that type of compressed environment right now, you have to build your world, your entire algorithm, using less than 100 operations. I mean, it's fascinating. And so that really lays the groundwork for understanding how the choices we make at a hardware and software level ripple through and impact the algorithm. And what I realized was the following, is that even though I was stumbling and kind of peppering all these amazing teams at Google with these questions, historically, these communities have evolved totally in separation. For example, I would challenge anyone, go read a systems paper tonight. If you're an algorithms researcher, go read a systems paper. And please let me know if you fully comprehend it. It is a totally different body of knowledge, manner of publishing, manner of engaging. And that's because for a lot of computer science history, there's been very little incentive for these three groups: algorithms, software, and hardware to work together. And that is a lot of what the hardware lottery is about. The hardware lottery really starts with this grumpy statement, which is that for computer science history, hardware and software have frequently determined which ideas succeed and fail. And then a lot of the essay is unpacking that claim and saying the reason why we say this is that we know from early computer science history there have been all these occasions where the idea could not be executed. There was huge lags. So with the analytical machine close to a century, but even more recently with deep neural networks, because the idea was proposed, but we didn't have the hardware and software to operationalize it. The reason, oh, sorry, go ahead, Charles. You looked like you were going to say something.
Oh, no, I was just thinking.
You were just nodding. Okay.
Yeah.
Excellent. Well, I appreciate the nodding as I go through this. It's like a good feedback loop. And I think what's interesting is now we've laid the scene. So this is why I got into this essay. And a lot of what the first part is essentially talking about examples of this hardware lottery. The reason why I finally felt obliged to put it on archive, and it's quite funny because I put it on archive and this is very different from a typical research paper. So in many ways it's been quite fun to see the variety of audience who is connected with it. But the reason why I felt compelled to do that was the second part of the essay, which is that really the position of this paper is that while the hardware lottery has existed and it's dominated a lot of the rate of computer science progress, I posit that this in fact will become a bigger gap between the winners and losers. And the reason why is that our ecosystem of software and hardware is becoming even more fragmented. So we have kind of, as the last talk very well captured, we're starting to get all these different tooling kits at the software level, but also with the advent of domain specialized hardware. And this is hardware which, in an interesting way, should have solved for the pain points of us developing in isolation. It's hardware where essentially the focus is on specializing for specific algorithms. But the tricky part is that because it's specializing for certain algorithms, if another new algorithm comes along, it becomes harder to take that hardware and show that the new algorithm is a success. And when you have this, when you have essentially more combinations, but more locked-in combinations, and more effort going to certain, it becomes more costly to stray off the path, the beaten path of research. And right now, the beaten path of research is deep neural networks. So deep neural networks came around in 2012. Essentially, it was an overnight empirical success. It was one of those rare snapshots in computer science history where everyone overnight switched. And that was mainly because there was not the hardware prior to 2012. There had been iterations throughout the 2000s, but it was really GPUs coming along that allowed deep neural networks to train to the depth that they needed to show the empirical success. And for subsequent years, essentially particularly for computer vision and then and now across multiple domains, that is what is dominated. But there are clear limitations to deep neural networks, and there are clear signs that perhaps this is not the only way forward, particularly and there's almost two lenses here. So there are many clear commercial use cases of deep neural networks. So I think, Charles, you must bring a lot of people on your show who are really excited about how do we translate this breakthrough to commercial use cases. And I feel like there we're just it's like we're at the beginning of the road. It's super fun road ahead. There's many different domains that we haven't yet enabled. I mean, this is part of the motivation for resource-constrained environments, why I'm so interested in that. But there's another side, which is that in terms of an overarching goal of furthering this history of artificial intelligence research, the clear limitations of deep neural networks are starting to show. One of which is that it's becoming increasingly costly to scale. They're very expensive models in the sense that we're throwing a lot of parameters at a problem for not much return. A good example of this is the enormous growth in weights of deep neural networks. So you go from inception v3 to inception v4, it's almost a doubling of weights, but you only get an extra 2 percentage points in test accuracy. So both the training cost as well as the decreasing returns are becoming apparent. But furthermore, there's key issues to deep neural networks that we don't see in other forms of biological intelligence, such as deep neural networks evidence catastrophic forgetting, which is a very snazzy word to mean that when you train deep neural networks on new data, it tends to forget what it was taught before. Which humans don't have, because we show this remarkable versatility to pick up skills over the course of our lifetime while retaining skills that we may even have learned years ago. I think the other thing is that we show far more efficiency in terms of how we treat examples. So we often don't need to do a full forward and backward pass. In fact, most of what you're seeing right now, what I'm seeing right now, unless you do something crazy, like put your hand out here, is virtual simulation. Like I've already simulated what I expect you to do, and if that matches what my prediction is, I don't do a full forward pass of the inputs. And that's hugely efficient. It makes us able to do far more with far less. Our brain runs on the power of an electric shaver razor, and in contrast, GPT-3 costs $12 million to train. So all this to say, the limits of our current approach, the cliff of this hardware, software, algorithm combination are becoming apparent. And that's why this was fun to write and to think about, because it also, in my own mind, forced me to think about what I would recommend to solve for this cliff. But I'm going to pause there because I kind of talked a bit and hopefully gave a flavor of the work. And maybe I'll return it to you. And
yeah, thanks for that context, both sort of, how you came to like thinking about this problem and how you were thinking about it as, at a meta level. And in addition, sort of what your presentation of the contents of the paper is all, very interesting. One thing that really stuck out to me, I think, was you referred a couple of times to like to biological intelligence as like an alternative, as a source for ideas. And so my PhD is in neuroscience. I was at the Redwood Center for Theoretical Neuroscience, which is a group that does a lot of sort of looking to biology for inspiration to design algorithms. And I think, we often found there's kind of this struggle that a lot of people sort of feel, we learn to fly not by putting feathers on our wings, but by building jet engines. That's like a refrain you hear often from folks who are, especially folks who are working in deep learning and don't think that we should get our inspiration from biological systems. So I'm curious, what do you think? You mentioned predictive coding. I guess what other kinds of things do you think we can learn? Like, is it, event-based, spike-based models? Is it additional recurrence? Is it, what is it that you think biological intelligence can offer us as ways forward?
I think it offers us counterfactual data points, right? So right now, essentially, because this journey, this mission is so recent. So the Dartmouth Council was in 1946, and since then, that was what really pulled together people first talking about transferring to machines, skills normally reserved for humans. But we're still less than a century out from when that occurred. And in many ways, our search space is very small. We have And it's primarily dictated, what combination of ideas we can explore is primarily dictated by the stack, by the degrees of freedom that we lose as we first choose our hardware, then we choose our software. So my point with biological examples is not to suggest this is the way. And in fact, I think I would be a foolish person to make that bet, particularly documented like this. But it's to say that we at least know there are things that we biologically do differently that we are not doing with our current models. And the reason why that's important is that domain specialized hardware is really, really, really tailored to our current models. Essentially, the emphasis there is on making our current models commercially viable with a distant secondary consideration, distant, being future research directions. And so while I'm not going to take the bet that deep neural networks are not the way forward, I'm going to suggest that there are clearly multiple ways of mapping the world. For example, I work in computer vision a lot, thinking about the interpretability of computer vision as well as the compression of computer vision models. Computer vision and CNNs in particular are interesting because we often, for interpretability, expect these models to extract importance in the same way that we do. However, there's no such constraint that we train these models with to do that. In many ways, the reason why CNNs demonstrate this remarkable ability, particularly on medical images, to extract features that we can, is that our vision is log scale on purpose. We need a noticeable change in order to register something happening for our own robustness. There's no such constraint on deep neural networks for the same thing. In fact, that's why deep neural networks can extract these pixel-wise differences. And so things like that, I often think it's not so much that we articulate it as this is the way, it's more that we need to increase our search space and make it cheaper to explore that search space.
I see. I do want to ask one more question before we pass over to the variance of gradient work, which is like what I saw as a big impediment was basically a certain amount of like conservatism or on the part of granting agencies and of large companies that could possibly fund the kind of research necessary to break us out of like this current iteration of the hardware lottery, that they were, like on the one hand, you've got people doing really exciting new work constantly with neural networks. And then on the other hand, you have people who still are in the world of sort of, toy models saying, oh, I think the, oscillation-based or optical networks or, spiking networks are really cool, and that's what we should be spending money on. So do you think that there's a way that these institutions can be convinced at this, scale necessary to break us out of this lottery? Or do you think that, do you have a sort of pessimistic view that this is just a feature of the way research is done and we aren't going to break out of it?
So it is a feature of how research is done. We're never going to eliminate the hardware lottery. I think the main point of the essay is that right now it dominates computer science progress. And the degree to which it dominates is problematic. So in order for it to dominate less, we need to make it quicker to iterate. And quicker to iterate in the hardware space is extremely expensive. You need a lot of bucks of whatever currency denomination you want to talk in. And that is the tricky part. So there needs to be more support from essentially, I would say, governments, because private sector is always going to lean towards hardware that's optimized for commercial use cases. And that has its benefits too. You need, a mix of different people who are designing and thinking about these problems. But right now, the gap in terms of government expenditure in this area is painful. It's kind of fascinating. I think even the discrepancy between US expenditure and Chinese expenditure, it's thrown so much more into this ring than the US has. And so it's really interesting to look at those dynamics as well. Software engineers have the highest burden on their shoulders. And at this point, we're just going to end up showing a slide from the other presentation, but that's okay, because I think these topics are interesting. And when you said let's do two, the writing was on the wall. I was like, but no, it's software engineers who have the biggest burden to play. and biggest role to play in many ways, because the tricky thing is that a lot of the bottleneck now is in the design of compilers, and it's also in the design of the software layers. And partly it's making us understand what is the cost of using different hardware, because right now it's just very costly to even try out different types of hardware. In my research flow, I basically have a single type of hardware that I use. If I need to release code and switch hardware so that I'm using a different type, it's like multiple days of switching out operations. It's not something I do experiment to experiment. And that's a great example of a pain point, which is really an engineering pain point. The secondary thing is that we just need better feedback loops. I mean, error messages at a hardware level are painful. I mean, as a researcher, I want to care about hardware, but I don't have the time to, because it really is not a precise enough feedback loop for it to be actionable. And I think that's another main point here, is that despite hardware and software mattering so much, researchers do not talk about it. And the reason why is that it's quite rational why we don't talk about it. It's because it's seen as something we can't change. It's seen as something so time consuming to try and influence that we almost abstract it away. And I think that that's the interesting part, is how can we make it cheaper for us to engage in that conversation. I am going to put up the slide because I do want my lovely co-author Chirag, he's my co-first author, and he's fantastic. So
I was honest to goodness really excited about this paper. So, you know, if you can stick around for an extra 5 minutes, we'll spend 10 minutes on it.
Oh, okay. Yeah, I'm happy to. I'll at least put this up while we, because we only have 3 minutes left. So we'll stay on the hardware lottery, and then I'll do a brief summary for the next, for people who want to stick around. But yeah, the paper with Chirag, who is my lovely co-first author, and this paper is about estimating example difficulty. And so I'm going to do a little bit of a hat switcheroo here. And I'm going to talk about really another property of beyond tested accuracy, which is how do we audit our models, and how do we surface an understanding of how the models learn a decision boundary to people who need to navigate and to make decisions about AI safety. And the big obstacle in terms of ranking examples by difficulty to date has been the computational cost. It's very expensive. And so the work with Chirag is really proposing a much cheaper measure to achieve this. In fact, what we leverage is the variance of the gradients during the training cycle as well. So it fits into your traditional training regime where you save checkpoints as you train. You can leverage those checkpoints to understand what examples are challenging and what are easy by looking at which gradients converge the fastest. And it turns out to be very effective at servicing the most problematic examples for human to take a look at, either for further annotation or to audit for accountability and fairness. So that was very jazzy. I think I got that under 2 minutes. Is that possible? That was quite a compact summary.
Yeah.
Yeah.
Well compressed, you know. So it makes me wonder what that perhaps forgot. Yeah, I mean, if you want to spend like a little bit talking about the maybe showing some of the results or the key figures of the paper, just in the you know, folks will stick around, I think, for a couple minutes, and we post these on YouTube afterwards, and folks I'm sure would be happy to sit through an extra.
I see. Okay, so I can go rogue. Okay, excellent.
You can do whatever.
Okay,
yeah.
I'll go rogue. Maybe I'll even squeeze in 8 minutes. That's fun.
All right.
Yeah, absolutely. And a lot of what this research is focused on, and I guess I already spoke to this, but my research is really on this area of going beyond tested accuracy. And that's because we know that, and perhaps I'll just present this. Lovely. Okay, we're rolling. And a lot of the motivation for this work is that we often have accuracy without true learning. And so top-line metrics often hide critical model behavior, and that's really the role of these interpretability tools, in my mind, is to provide intuition and to provide meaningful examples for humans to be able to audit a lot of the issues. And a lot of work to date on interpretability has focused on local explanations. And what is the difference? So local explanation, you may have seen a saliency map before. They're widely used by practitioners, where essentially, for a given example, you estimate what is important for the model prediction. So this is, I guess it's a sandwich. Is it a meat sandwich, perhaps? It's like a pulled meat, some variety of sandwich, and the model is highlighted, these parts of the sandwich as contributing the most to the model prediction. And the reason why a lot of work on interpretability has been limited to these single examples, there's actually a few reasons. So one is the high dimensional input space. So it's just so expensive to try and scale feature importance across a data set, because even a single image may have 250,000 features. And the other is that, in fact, a lot of the onus has been on providing single end user explanations. So for example, if I'm at a doctor's office, I'm always going to want the explanation from my x-ray. And you can imagine multiple use cases in which you will always want to try and explain a single prediction. However, a lot of my earlier research was showing that essentially meaningful explanation does not always equate with reliable. And so you can have these saliency maps which look very meaningful, but can be easily manipulated. And in fact, we show that. We show that it can be manipulated to show a kitty imposed on top of a 7, which is fun. And we also did work which was showing that often these estimates of feature importance are no better than a random estimate. And so a lot of my recent research is focused on what next. What next is really thought about what happens after a human sees a saliency map. What actionable decision do they make? And if I were to ask you, Chris, essentially, what would you, Charles, what would you do when you saw this? You may actually struggle to make a decision. Is this a good saliency map, or is this a bad saliency map? In fact, you may want to look at additional saliency maps. And this is normal because a lot of our understanding of what is good or bad is relative. This is where it becomes tricky, because can a human inspect all the saliency maps of a data set, particularly with training data sets now that are extremely large? And so really this question of how do we surface what is important for a domain expert to understand, and particularly to surface a tractable subset, something that they can actually, within their annotation budget or inspection budget, be able to understand the behavior of the model. And this is the work with Chirag, who's my lovely collaborator. And really, the work revolves around how do we understand how feature importance forms over the course of training. So what you see here is there's very interesting research which suggests that there's distinct stages to training. So, for example, the chart on your left, I believe, yes, your left, is critical learning periods in deep neural networks. And so, in fact, this is a chart which shows that, in fact, if you train a model on corrupted data early on, it can no longer converge to better data later on, suggesting that there's some special attributes at early stage of training that determine how feature importance is formed. And we leverage this fact in this work. And in fact, what we say is, well, the hypothesis that we formulate is that for easy examples, the model will converge quickly on a fairly narrow range of gradients because it's consistently predicting the same prediction for that image. For hard examples, the model is trying to place the image at different parts of the decision boundary. And so, in fact, it will keep on oscillating the gradients, and we'll see higher average variance in the gradients. And so that's what we do. We look at checkpoints over the course of training in the same way that you would typically save your checkpoints in a normal training regime. And then we compute the input gradients, and we look at the variance of that image consistently over the course of training. And what we find is that it actually provides a really useful ranking of each class. And how do we evaluate that? So we qualitatively visualize the lowest VOG and the highest, and you can kind of see that they have these very distinct semantic clustering traits. So lowest VOG has these much more, I guess, centered, crisp images. Highest VOG is much more cluttered. But we also look qualitatively And we see that VOG is much more effective at discriminating between easy and challenging examples. So this is CFAR 100, and this is the bottom 10. So the bottom 10 percentile of VOG, and you can see it's much lower test set accuracy. And then, oh, apologies. And then this is the top 10 percentile, and you can see it's much higher test set accuracy. And so VOG is doing a great job of ranking the entire data set so that it surfaces as high score the most difficult examples to evaluate. And the benefits is that it really fits into your practitioner's current workflow, and you can leverage the checkpoint stored across training. I'm not going to talk about these other two works, which essentially try and get at this common theme of ranking and surfacing, but a lot of it is how do we leverage differences in models to surface what is worthy of auditing, which is a theme that I think is very important for interpretability, particularly as we try and apply it to production systems and figure out how to equip humans to check before they deploy if there are any potential issues with the model. So I'm going to stop there, and maybe I'll turn it back over to you, Charles.
Yeah, I think maybe just a couple of questions before we go. You know, I at least want to catch the U.S. presidential debate. Hopefully, they'll discuss whether how to appropriately respond to the hardware lottery and the need for additional investment in hardware. But I don't have high hopes that will be discussed. A question from Swear Shah. Do you know whether this approach of looking at variance and gradients, would this work for, models like semantic segmentation, or do you think this is something that might be sort of more specific to, classification and computer vision?
You can use it for semantic segmentation. The formulation just has to be changed a little because you end up predicting, an area. But actually, there's an internal team at Google right now that's testing it for segmentation tasks. So partly, I believe we will be open sourcing the code within the next 2 weeks. So I think we could also include a variant for that.
Great. Yeah, it'd be interesting to see. I guess the one other domain in which it can often be hard to translate from, from computer vision is the reinforcement learning, like deep reinforcement learning. I feel like every time I look at the papers in that field, they're using different optimizers and they're thinking about the problems very differently. So you think that looking at some sort of variance of reward or variance of prediction error or something like that might be able to translate this to figure out, where RL agents are most confused?
In some ways, the primary hypothesis of this is that the gradient itself, the variance of it, the degree to which it changes at different intervals is indicative of uncertainty. And that applies to any model that's trained in a gradient optimization-based approach, which is kind of all of them at this point, or at least a lot of state-of-art models in different fields. So I think it's interesting to think about. There you naturally have just a lot more noise to begin with, because essentially you also have task switching, but also the intervals at which you do task switching are often not predetermined. So the one caveat I would say is that we do class normalized variance of gradients, because essentially we look at class rankings. It's far less clear how you would do that in a setting where you don't have a distinct class or you don't have a crisp sense of demarcation. But that's kind of cool to think about, because perhaps you don't need that. Maybe you can just use the raw variance. So yeah, I see you nodding, Charles. If you want to take this up as a research direction, let me know.
I don't know. I don't have much time for research these days. I'm mostly doing webinars in which I ask people about their really cool research. So there's not so much time.
Yeah, fair. You can't optimize for it all. Something has to give.
I do want to, I guess I got one more question before I let you go. So one thing I notice when I look at the distributions of my gradients, these are marginal distributions, so not class specific. But I see this incredible degree of sparsity. I see almost like a Cauchy or a Laplace distribution where it's almost all zero, and then there's heavy tails.
Yeah.
Do you think that the higher moments like skew and kurtosis have anything to say, or do you think that the variance of gradients basically captures all that there is to capture in those higher moments?
Well, in I guess in many ways what we're capturing with variance is time, right? So we're looking at different snapshots across training, which is really the information that's being conveyed. Because our primary assumption is that time, after a certain amount of time, the model has already learned the easy examples. And so that the variance will be downweighted by the convergence over time. And for hard, it will just keep on oscillating. So in that sense, I don't know if a single snapshot is competitive. That's partly why I think we had such cool clusterings, and it was so exciting because this is a far cheaper way to get at much more expensive ways that have attempted in the past to do this by looking at a single snapshot. Like there's a fantastic paper which was about influence functions, which is about single snapshot, but it's extremely costly. There's another paper about C-score, which is super interesting, but it requires like 20,000 retraining of your model. So this is in many ways, the exciting part of this is that it's a cheap proxy to get at the single snapshot, much more complex formulation of the ranking.
Gotcha. Yeah. Yeah. Maybe no need to overcomplicate it by calculating, say, the entropy of the gradient, when you can probably well approximate the behavior of that with something like the variance. Thank you so much, Sara, for coming and being willing to talk about your work and answer everyone's questions. It was a real pleasure.
Yeah, it was lovely. Yeah, nice chatting. Bye, Charles.
Take care.